Hello everyone, thank you for coming to our paper presentation. Today I would like to present our research of two-chamber soft actuator with expansion limit line for force enhancement. Now let me start my presentation. Contents are as follows. First, I will provide some background information and explore the design of soft actuators. Then, I will explain the manufacturing process and present our experimental result. Finally, I will conclude with the performance of a two-chamber soft actuator. Unlike conventional lead robot, soft robot can interact with the environment and operate safely with unexpected contact or delicate object. So, the soft robots are used in various fields such as underwater robot, walking robot, hand assistant, and industrial soft gripper for food picking because of high compliance and stability through flexibility. Soft actuators that can perform three-dimensional movement like bending, twisting, and spiral trajectory. These movements are being developed to perform more variance tasks beyond simple bending. A two-chamber soft actuator can perform three-dimensional movements with minimum number of chambers. However, conventional soft actuator has an expansion limit layer that can obtain more tip-force but hinder twisting motion. In this study, we propose a two-chamber unit actuator to which an expansion limit line is applied to obtain a force gain without rotational motion limitation due to the expansion limit line. We propose three design of 2 degrees of freedom soft actuator consists of two chambers. This design that the exist or modified soft actuator can bend when pressure is applied to both chambers and rotate when pressure is applied to one chamber. This design has different middle wall position and chamber shape. Type 1 has no middle wall between two chambers. Type 2 has middle wall only in the chamber. And Type 3 has middle wall along the entire length. We confirm performance of soft actuator through finite element analysis. When a pressure of 0 to 80 kPa was input to one chamber or two chambers, we investigating twisting or bending angle of all types soft actuator with FEA. The maximum twisting angle and bending angle of each model can be obtained from the tip position. As a result, we comparing bending and twisting motion. Type 1 is most suitable model in 2 degrees of freedom soft actuator. Therefore, by attaching the EL line to the Type 1, we check the effect of the EL line on the operate through FEA. The EL line of Type 1 is attached utilizing nylon and polycarbonate, which are used to restrict the deformation of the soft actuator's bottom. Performance in bending and twisting, as well as tip force, varies depending on the width and material of the EL line through FEA. Therefore, 1 mm nylon, which exhibit greater rotation and increase in force upon attachment, was selected. The mold was designed for the fabrication of TPA using a 3D printer. Our soft actuator parts are largely divided into a bottom part and actuator part. After fabricate two parts, use uncured silicone to bond them together. Using adhesive for silicone, nylon is attached to back of actuator to make EL line. Left figure shows the setup of an experiment to measure the bending and twisting of TPA. To observe the bending and twisting of the TPA, it was installed vertically and the experiment was recorded through a camera. In experimental result, bending angle was reduced by 90.8% compared to without airline at the same pressure. But in the maximum twisting angle was increased by 22.8% compared to without airline. So it was confirmed that a bending angle decreased but increase in the maximum twisting angle compared to without airline. This picture shows experimental setup to investigate the effect of the tip force and grasping force according to with and without airline. In tip force experimental result, when the same condition, the actuator with airline can produce up to 1.5 times greater force compared to the actuator without airline. Similarly, the actuator with the airline could support a load 5 times greater than without airline. This result confirms that with airline, it is possible to obtain a greater force by limiting the expansion of the bottom and obtain more stiffness against external force of the bottom part. We fabricate a gripper consist 3 TPAs with airline, arrange in parallel and position the gripper in the direction of gravity. The grasping experiment was conducted by holding 6 objects in 3 categories: cylinder, cuboid, and tool. At 70 kPa, the gripper can successfully hold plastic bottle with weight of up to 500 grams and hold pressure objects like fruits. The result of rotational motion experiment confirmed that the soft gripper consists of 3 actuators can rotate the object at a speed of 12.3 degrees per second. In addition, we conducted experiments on rotational motion using various objects on the platform as well as exploring lifting motion. These include a paper cup with a 100 gram weight, a tangerine of fruits, a pencil holder, and a hemisphere model. In this study, we propose a 2-chamber unit actuator to which expansion limit line is applied to obtain a force gain without limitation on rotational motion due to expansion limit layer. We performed finite element analysis on 3 designs that can rotate and bend using 2 chambers to find the optimal design. The effects on twisting, bending, and tip force according to the width of the airline on select design were then verified through FEA. The airline is applied to obtain a force gain without a limitation on rotational motion. In the case with the airline, the maximum twisting angle is 22.8% larger. The tip force is 1.45 times larger, and the grip force is 5 times larger than without the airline. The gripper can rotate the object at a speed of 12.3 degrees per second. In addition, experiment with rotational motion with various objects on perform and lift up motion. Thank you for your attention. If you have a question or feedback, please feel free to share it. Thank you.